extremely powerful tool that can be used to analyze and visualize many vector and raster data. Borehole data can be used to image many fundamental geological structures, including bedrock units, faults, and faults. Regional analysis and large-scale analysis are all applicable. Large-scale air emission data can also be visualized. Interpolating tools are used for creating DEM layers where data are insufficient. Thickness and elevation DEM layers from provided borehole data is vital in this project. Attention towards air quality is crucial due to its adverse effect on human health and environment. Moreover, it exacerbates global warming and climate change crisis, having far-reaching impact on both human societies and ecosystems. To improve air quality in London, we will examine the primary air pollutants including nitrogen oxide, PM2.5, and carbon dioxide, identify their sources, and provide mitigation solutions. Emissions data from the pollutants in UK have similar patterns. All rebuilt cities and roads have higher emissions compared to the rural areas, with southeast UK emitting more than northwest, the London having the highest emissions overall. The high traffic congestion, population density, industrial demand, and favorable infrastructure and resource make London one of the busiest regions. As the capital, it attracts global connections at BC's airport as to the air pollution problem, which is further exacerbated by the city's location surrounded by hills and trap pollutants. London's CO2 emissions are highest in central areas, particularly Zone 1 and Heathrow, while emissions in other boroughs on M225 are moderate. PM2.5 emissions are also highest in central London, with no significant decrease in surrounding regions, indicating a widespread distribution from diverse sources. Nitrogen oxide emissions are highest in central London and Heathrow, with road emissions being slightly lower but still high, driven mainly by transportation. Therefore, the sources of air pollutants greatly impact the distribution of emissions and regional air quality. These sources can be broadly categorized into transport, industrial and commercial, domestic, and miscellaneous. Road transportation is the major contributor to transport emissions. Heat and power generation as well as construction dominate industrial commercial emissions. Domestic emissions come primarily from heat and power generation and biomass. Miscellaneous emissions are mainly agriculture in the region. In 2019, London's CO2 emissions were largely contributed by three sources with similar contributions, with road emissions from transport accounting for one-third in total. 70% of nitrogen oxide emissions came from transport. 50% was from road emissions, highlighting significance in nitrogen oxide emissions. PM2.5 emissions were largely driven by industrial and transport sources, contributing 36% and 38% respectively to total emission. The largest contributor among three selected sources were road emissions from the transport. Diesel and petrol vehicles are the main contributors to road emissions, buses, coaches, and EV being the minor contributors. Since majority of the London tube lines are fully electrified, while only the outer section of some lines are diesel operated. Constructing a new underground line would reduce both transportation emissions, car bus demand, thus lowering overall road emissions. The lack of up-to-date information in both data sources, which may result in outdated information being used. Incomplete data from certain sectors, such as waste sector emission data, can impact data quality. Different air pollutants have various methods of sampling and measuring. Improving the reliability of analysis and reducing uncertainties can be achieved by selecting most recent data from a consistent inventory, considering the varying methods of measuring for different air pollutants. Borehole data was provided by BGS. 1,122 boreholes were selected based on several criteria, including data quality and consistency. The heat map of borehole data shows the distribution concentration of selected data in the analysis area, revealing a random but uneven pattern. The highest density in the city of London, followed by Westminster. Most of the data concentrated in East and Central London. Notably, the relatively low borehole density in West London is where the London clay formation is thickest, highlighting the significance of this formation for tunneling work. The thickness of London clay affects the borehole distribution since borehole data is highly involved in geological modeling for examining geological structures. Its efficiency is directly related to the efficiency and the accessibility of the geological analysis. Within the study area, the City of London has the highest spatial density, while Wentworth has the lowest density of 0. Westminster has the most boreholes drilled, but its large areas result in a lower spatial density compared to London. The average spatial density of the analyzed area is 22.06, similar to Camden. 6 geological units from the Pleiadian succession are well documented in London Basin and dominate the facies beneath it. A simplified stratigraphic log is constructed. Main ground is the thinnest, while chalk is the thickest. The thickness of the London clay varies greatly, with the thickest layer reaching almost 80 meters in southwestern London and gradually thinning to zero in the southeast. The clay thickness again across London, running parallel to the axis of London Basin. However, it slightly thins both north and southwards, further demonstrating the presence of syncline in central London. The thickness of thinnest sand increases considerably in the southeast, while Lambeth is relatively consistent with an average thickness of 28 meters. Only 6 boreholes have been drilled in the base of chalk units, revealing an average thickness of 186 meters. London's geological structure is characterized by 2 major faults in the east-west trending syncline. The fault lies between Wembley and Streatham and at Greenwich. The city rests on the syncline axis that constitutes majority of London Basin. It was formed during Oligocene and Miocene during Alpine orogeny event. Minor faults and faults also exist on it. The elevation dm of the base of the geological unit can provide insights of this west plunging syncformal structure at the base of London clay. It extends across the center of London, becoming more pronounced with depth. The absence of this U-shaped pattern in the gravel unit and the presence in the London clay indicates that the structure was formed before gravel but after London clay. This west plunging is further supported by the low elevation in the southwest London. BGS imported geological data gives a comprehensive overview of London geology, including fault data and superficial bedrock data. The Wimbledon and Greenwich faults are prominently highlighted. The property of materials of rock are essential for tunneling work. It exists evaluating geological risk and determining drillability by considering factors such as rock type, strength, hardness, unit discontinuities, porosity, and shear strength. Impermeability of this stiff silty London clay and its high shear strength, highlighting its role in tunneling work, is also lithologically monotonous. This makes drilling safer and more efficient. However, skull horrors of the intrusion of the strata below can lead to discontinuity of London clay. The Lambeth group shows the significant lateral and vertical variations in its main depositional surfaces, such as silty sands, shelly beds, limestone beds, and sandy flank gravels. The variability of this water-saturated sand and gravel making tunneling complex and uncertain. This high permeability of the low shear strength of the thinnest formation result in water infiltration and instability, making it unsuitable for tunneling. The presence of multiple subvertical faults and erosive features in the chalk aquifer adds further complexity to tunneling. The triply 2D cross-section reveals the majority of stations transverse the London clay formation and follow topography. The line was designed to align with the base of London clay, as engineers consider it optimal for tunneling. Piccadilly line connects West Central and North London, digging into the Lambeth group and leaving the London clay formation from Covent Garden Station due to thin and absent London clay formation. The line also runs along the syncline axis between Earls Court and Covent Garden stations, with clear westward dip evident in the cross-section. The Northern Bank branch line passes through northeast London, where it bolts into Lambeth Group as London clay is absent. It's evident that water level is notably high beneath Old Street Station due to corrosion from highly oxidated groundwater. This information can be visualized in a 3D model using QGIS. Tube lines and bedrocks are incorporated to present an overview of London underground tunneling work. Most of the tunnel travel through London clay formation, partly of them take into Lambeth in northeast and central London. Only very little part of Piccadilly line cutting through very northeast London. To effectively address future tunneling challenges in London, crucial considerations must be made. Risks such as soil uplift, erosion, clay loss, and water-saturated sand and gravel must be mitigated through a thorough understanding of the geological conditions. This can be achieved through borehole drilling and the use of techniques like electrical resistivity imaging and seismic refraction to gather subsurface and groundwater information. The ground-based radar method can also provide valuable insight. Up-to-date data can be obtained from recent deeper engineering projects like CDRL. The existence of minor subvertical faults and the perfect anticlines in East London must also be taken into account. Here are the other considerations that we need to think of. The planned new London Underground line will travel through existing platform stations. Major stations are Paddington, Marble Arch, Hyde Park Corner, Victoria, Waterloo, Bank, and Canada Water Station. This line will be fully through London clay as shown from the 2D cross-section, and also the high emission stations. It also will share the burden of the high population exposure stations. However, risk of high water levels in Canada Water Station need to be considered, as well as this discontinuity of London clay.
Thank you.